It's open 30 seconds allowed.
Okay, let's start. Hello everybody, my name is Laurence. I am chairman of the Advanced Organic Fisheries Group. Today we have the last meeting of this season, 2018-19, and presentations are by Steen, Dupont, and Laurence Livermore on treasure trove of nature, the advances and challenges of digitising natural history specimens.
Cool. Thank you very much for inviting me, first of all. I am Steen, that's Laurence. Thanks for letting me be here. We're going to be talking a bit about the natural history and some of the stuff we have in it, some of the challenges we have with that stuff, and how we're dealing with that. But I thought, first of all, it was probably a good idea just to have a look at the building. I presume you guys have, most of you have probably seen this building. It's a pretty old building. It was built in 1981, commissioned by a man called Richard Owens, and it was actually 1881. Sorry, 1881. Thank you. That would not make it very old. It was actually paid for by the people and built by a man called Alfred Wallace. And it was built as a cathedral to natural science, which is a bit odd, seeing as you've got science and you usually have religion. But it is actually built as a cathedral, as an homage to natural history. And it is very much so. When you walk into it, it's grand, it's big, it's got stained glass and things like that. But within it, it contains all of the collections that we have, which have been collected over 250 years and represents 4.5 billion years of life. It's quite impressive. Of course, those collections, if you walk into the museum and you have a walk around there, you'll see about 30,000 items which are on display. But in reality, we've got loads more. So if you have a look, you've got birds, you've got fishing tanks, you've got dinosaurs. Of course, most people associate dinosaurs with the museum. We've got furry rocks, believe it or not. You can try to find it when you go to the museum. And we've got loads of things in spirit. So we probably have more flavored spirits than most bars in London. We just tend to drink them. And we've also got pinned insects, plants on leaves, and all of those contain data. So let's just have a look, just to get a sense of what's in that collection. Primarily what we have is we have microscope slides, we've got pinned insects, and we've got plants on sheets of paper, herbarium. That makes up about 90% of our collection. If you look at the numbers, that's 2.5 million slides there. It's 25 million pinned insects, and it's about 2.8 million herbarium sheets. So it's quite sizable. We estimate we have about 18 million things in the museum. Right? That's a lot, especially if you're trying to keep track of it using index cards and catalogs. That makes it very difficult.
How does that size compare with the amount that's out there in the world?
Oh God, it's
in terms of representing the entire
25 million insects sounds small to me.
There's about 1 million described species of insect, but I'm not sure what proportion we've got representation. It varies enormously by group. I think the beetles are one of the best represented by species.
So the beetles are one of the biggest groups and the best represented, the butterflies. And the butterflies purely because they're pretty and they've been collected for so long. The beetles as well, because we have had some amazing collectors throughout time and have some now. How it represents to real life, honestly, I wouldn't know, because it is, especially within entomology, you can actually go to Hyde Park and discover new species for science.
Probably not of an insect.
Of an insect, you just have to go down to go up to parasitic wasps, because not enough people have been looking at these things. You do have to be a specialist and have spent many, many, many years to actually know that this is something special. But yes, I wouldn't know how it actually compares. So, moving on. Index cards, catalogs. We do have a collection management system, and I thought I'd just give you a bit of a sense of what that looks like. Currently, we have 232 million records in that management system. Most of it is an audit, which we can discard, because we do use that, because we have simple changes in our database that can change tens of thousands of records. So we do need to be able to go back through and see how things change. If we look at the actual record count, we've got about 30 million record counts, which, sorry, this is not really entirely saying we've got about 30 million record counts, but we also have about 8 million that represent actual specimens with all the data around it. So this is not just the individual, this is a species. If this species was collected here as part of this. And if we look at some of the data, that's our system. Not very big on the face of it. But within that system, we've got all our media and asset management. We've also got all our 3D modeling scans that are meant to be there. So jointly, when you look at the data, it is massive. And what we haven't looked at here, which Laurence mentioned earlier, is all the DNA data. And you'd be surprised by how much space 2 lines of code with 4 letters can take. When you start adding that up to full genomes, it
makes that look like a drop in the ocean, piddly amounts of data.
We're talking about, I think it was hundreds of petabytes of that, which is crazy. Now, sorry, did I just skip ahead? No, I didn't. Now, I wanted to highlight a few challenges before we start getting into the data, the digital realm, which Laurence is going to jump onto later on in the talk. Because before we even start moving into digitizing and make all our data digital, we've already got issues with missing data, or data that's mid-1968. It's mid-1968, but if you want to place it into a database properly and have it fixed and searchable, this little louse here lives on a dog. Dog is not really a term we use. That's just a dog. We've got scientific names for things. Where do you place it? And that little dot apparently means the person who made the slide, that dot had a significance.
The third stage nymphal instar.
But that requires the specialist who made the slide to have noted that somewhere, or for somebody to remember that that's how he did it, to actually get that data in. So there's huge data problems. We've also got multiple schemas, because we've got botany, entomology, we've got zoology. They all use their own systems. They all record their data in specific ways, and they've done so for hundreds and hundreds of years. So they're not, of course, they're not just going to change how they've done that over hundreds of years. The system, to some extent, has to accommodate that, which is quite a big challenge. What we're talking about databases. And, well, disparity between the sciences, that's what we're talking about here. And we've got interpretation and non-interpretation. So some people want verbatim data that is on the label or about the specimen. Some people actually, some sciences have to interpret that data and add an extra layer of what they believe this is. If we talk about fossils, for example, people who look at fossils, one specialist may say it's this, another specialist may say it's that. They might actually be just as credible based on the evidence that they have. So the interpretations are meant to be in the database as well, depending on who's actually putting the data in. So that's a bit about the museum and the data, the collection we have in there. And I just want to summarize it before we get to what we do on the program that we have within the museum. So we've got lots of stuff. It's all very different, all the stuff we have. Not much of it is represented in the actual database. It's in the collections, in the physical form, but not in the digital form. So to address that, 5 years ago we started, the museum started a digitization program to digitize everything. Remember I said 18 million things. To tackle the variation that we have within specimens, what we need to do now is actually ramp up those processes and workflows that we have to industrial levels to just make a dent in what we're doing. And of course, we have some challenges along the way, which I'm going to talk about. So the Digital Collections Program, which is where we sit, where we work, was decided that digital was the strategy for the museum. We would digitize 80 million things within the museum. And to make that accessible to the global community to use that data for research and other things as they saw fit. It's all made openly available online for people to use. To create a foundation for advancing science and for using the data and inventing new cool things to do. And that's where we come in. So myself and Laurence are project managers within the Digital Collections Program, and we've both been very closely related to entomology and done research in that. I deal mostly with infrastructure on the museum side, so the museum database, some of the standards within the museum, some of the decision governance groups within the museum as well, and I build hardware. I build digitization equipment, so imaging equipment for the museums to get that physical data into a digital form. Laurence, I hand most of what I do over to Laurence. Laurence is the innovation manager, so he deals with designing the workflows, making that progression from physical to digital and into our database systems possible, and working with all the code in the front end systems that we have. So he's going to get into that.
Not a developer though.
It's not a developer. Now, as an organization, in any organization, when you talk digital and technology, it gets a bit messy. Because all departments, everybody thinks they've got a bit of digital and a bit of technology in them. So actually our governance structure, this is where our program sits, is a bit messy. And it's good and bad. Because we're a change program. When you're a change program, it's good to have your fingers in everything, because you can pull the right strings, make the right decisions. But change is always hard, because you have to get people to follow you on change. And if you've got too many people at the beginning, if you've got an idea you want to change the world, if you've got too many people there, they're going to ruin your idea. You have to make that idea cling and work before you grow it. So it's a good and bad thing how the organization works. Right. 80 million things. Where do we start? What do we choose? I mean, is it birds? Is it dinosaurs? Is it insects? First of all, it's a cultural change. It's about making the organization want to make our collections digital. It's about developing processes and standards to make sure that when we do these things, they're done right, so that we can be used down the line and for the future. It's about practical cost and time. Imagine it's costing us, I think, a bit more than £1 for an insect specimen.
Sounds like a sweet spot. I'm trying to get everything under £1 because it sounds good.
But even then, if you add it up to the amount of specimens we have, it's quite a bit of money. So yeah, it's about expertise. We've got specialists sitting at the museum who probably don't want us to touch half their specimens because we have to be trained to actually do that. So we do have people who are trained in handling the specimens. And it's about prioritization. Which parts of the collection are actually being used for research? Which ones would people want to pay for to see? That's a different one. Or which ones would have an impact or a public relations impact for us? Because we can't just go from one end to the other, because big parts of the collection are not used. They're being stored, they're being preserved in boxes and drawers, but they're not actively being used. Now, by digitizing, maybe somebody will use them, maybe somebody won't. So the question is, what do you do first? Do you take the stuff that we know is being used, provide it to the users, and they can go ahead and do that? Or do we provide the stuff that's not being used and say, hey, look, we have this as well? It's a bit of a gamble what you choose, and that's another thing that we have to look at. Why do we digitize? Well, we have things that change the way we think and how we look at the world. That's the missing link, the Archaeopteryx, between the dinosaurs and the birds. So the little dinosaur fed a chicken. Not scientific at all, but it's the Archaeopteryx. We've got Darwin's finches, which helped Darwin explain the natural selection and the adaptation that he did. And we've got the first Neanderthal skull, which was actually only discovered to be that 8 years after it was found. It was just sitting there. There was an amateur that actually found the Neanderthal skull, and they figured out what was the characteristics. They went back to the museum and said, hey, we actually have one. Which stand out, so that's the first one. We've also got the data that we have. Because it spans 250 years, we've got a bit of a time machine there. We can actually go back and look at species, because we have data from when they were collected and where they were collected. By amassing all that data, we can start looking at events that have impacted specific species or regions. So we can actually go in. This is a study based on 83,000 specimens, I think. Basically 83,000 species over 100 and something years. That actually shows that the global the climate change has had an impact on where these butterflies are and when they emerge. And we can do it. We can go back in time and look at that. It's not very many collections that can do that. We can also look at things like Zika virus and the associating vectors and look at where those are, and then we start to extrapolate who's in danger of being infected, which regions are actually high potential areas for being infected. So we can use the data. We can also have fun with the data. This is a mosaic of images from our specimens. This was just done to celebrate our 4 million specimens on the data portal, which Laurence is going to show. It's of Carl Linnaeus, who designed the natural history system, the Systema Naturae. Little side story, he also invented the index card, and he did that purely because at the 12th edition of his book, he had too many species to keep track of. So he needed a better system to keep track of his data, so he invented the index card, which was in somewhere, 1870, I'll look that up, 1760. I'm a century ahead of myself. The other thing we can do is that when we start to collect data, 3D data, for example, we can take a monstrosity like that, which is a bowhead skull, which is approximately 3 meters high. We can replicate it, and we can hand it around to people for education or researchers to actually have a look at it and measure things, or look at the conditions of the specimens. That is a bottlenose whale. So we can also do that. Now that's not just fun, that's also for teaching purposes and for research. What have we done so far? That was a long thing, that long story about why we do it. What have we done so far? We've mainly looked at plants and insects. And that's basically because the composition of the collection has that much of those, but it's also because plants on sheets are flat, they're easy to image, they're quite good to get started with, and because we have about 25 to 30 million specimens of pinned insects, once we've pinned that word slow down, then we can start progressing that, making that faster, and we will not run out of specimens. We can keep building prototypes.
Probably not in our lifetime.
Not in our lifetime. I'll give it back on to my son. So those are the two that we've mainly focused on, and slides, because again, slides are thin and flat, so you can take images. So how do we go about doing this? Well, digitization, first of all, means a lot of things. To us, it means anything from atom to bit, so taking the transition from atom to bit. For DCP, our program, it's mainly broad and thin. It's about showing and inventorying the collection and making that information available first. It's not about doing research imaging, which is taking obscure images of very specific parts of your specimen to prove something for research. It's about the broader picture. It doesn't help us, it makes the problem bigger. But that is how our program is trying to get that data. This is a typical specimen that's been digitized. So this is a bird wing. These are that big, quite valuable. And as you can see, once it's digitized, we have an image. We've got all the labels right down there. We've got a barcode, which serves a very specific purpose, which Laurence is going to talk about. We've got most of the data that's actually on the labels. We've got all the data, in fact. Location, collection event, who collected it. We've also got the record, the specific numbers within the database. Since that, we've got a bit about the sex, a bit about the stage of it. We've got external links as well to some of the external repositories around the world to make sure that they're also available there. The way we do that is quite straightforward. Find something in the collection,
I think it's straightforward.
which is extremely hard because we don't know much about our collection. So you go hunting for all the specimens, especially if somebody's paying you to do a project about something specific that is located around the collection and not specific. So let's say we were given a collection by someone that had beetles, butterflies, and weevils. And the curators for those specific groups decided to put those in specific areas of the collection. That's not recorded. When you go back and you try to digitize all that, you have to go around the drawers. We've only got 150,000 of those drawers that are categorized, but we've only got 150,000. You get the specimens, you take them to the imaging station, you remove all the labels, because the problem with insects is that you've got an insect, you've got a pin, you've got all the labels below it, so you can't just take an image from the top, because that obscures all the data. So you take all the data off, right? So you can line it up neatly together with the specimen. You then place the specimen in its holder, you take a snapshot, put the specimen back so you don't get lost, you get very angry when that happens. And then you start a completely different digital process with that image of extracting data, processing that image, and of course importing all that data into your collection management system, and then releasing that on. Now I'm going to focus, my last few slides, I'm going to focus on that part, and then Laurence is going to come in and deal with this part down here. Because as I mentioned earlier, I designed some of the imaging equipment and try to make the process as fast as I can. And I do that by trying to address problems that are usually problems that are there with the specimen, but also problems that pertain to the actual speed of digitization. So this Herbie here, which is herbarium imaging equipment, is designed to take images of this specific book, is about 300 years old. It's so brittle and so hard that it cannot open more than that. So so you can't get it flat, you can't just scan it. What you usually do is that you lower a glass plate down on top of the book to flatten the pages. I've got plant material on those pages, which is very brittle. If I did that, they'd just break and fall off. So
there's nuts and fruit in them as well.
There's nuts and fruits in them as well. Some of the pages are like that big. So essentially what I had to do was I had to put a camera on a swivel arm so I could get in there, very parallel to the page. I had to design a special book cradle to hold it so it doesn't fall apart. And I had to design a way of keeping the pages open, because all the methods that they use currently require strapping things to the pages or putting glass plates on top of it. It just doesn't work. So I designed these little hands in Lego. I do a lot of stuff in Lego. It's modular, it's quick, it's lightweight, it doesn't interact with most chemicals, so there's no problem actually touching a book like that, whereas if I was using lead or other plastics that could degrade or could transmit any chemicals, then that would be so child-friendly, basically, you couldn't hurt it also. So that's one way. The other one, talking about insect specimens, as I said, the labels are underneath the specimen, and it requires taking the labels off. And what if you couldn't, what if you didn't have to do that? What if you just image the specimen? Alice here, which is the angled label imaging capture equipment, I didn't name that. It's essentially 6 cameras that take 6 images of the specimen. And by doing that, we can then extract the data from the label without having to take it off. Laurence is going to explain more about how we do that. And then moving on from that, instead of having 6 cameras, we could just have 1 camera. Right? Because we've got good resolution now, we could essentially just have 1 camera with 6 mirror images that extracts all the images that I want and pulls out the labels and joins them together. So, and that's not speed, but that's bulking it up. Because if I have to spend 20 or 30K on that, because of the cameras, if I can then do it with 1 camera, that saves us a lot of money if you want to do it 6 times faster. That's another way of doing it. Another way of doing it is just imaging en masse. So let's skip the whole single specimen approach. Let's take full drawers of specimens and scan them all in one go. We've got enough resolution on the new scanners, quite impressive. So that's a little cut from there. That's perfectly doable to start looking at. So that little ring there is that zoomed in. To look at the characteristics that we need. And then we can start bulking things up, or making things faster as well. We can also start imaging other flat stuff, which is quite easy, some fossils. And we do this, so I said that we'd mainly used insects and herbaria to develop our workflows. Now we do that because those workflows usually translate well into other specimens. So here's a big fossil. You see the process is more or less the same. We line up all the labels there and we do a snapshot and we process it afterwards. So by focusing on one group, we're actually putting a lot of that knowledge into all the other groups, and we can start progressing with that. The last, I think this is two more slides here. The other option is to let go and be mobile. Lego, be mobile. It's essentially doing the imaging, as I mentioned earlier. Part of the thing that requires time is finding the specimens and moving them. Well, what if we don't have to move them? What if we can just walk into the collection, grab the specimen, digitize it then and there, and then have the data available and process it later? Well, we've got mobile phones now. If we devise setups where you just slide in there and you image it, and then that's that, because you've got it on your phone, you can send it on. Cameras are starting to get quite good. Or being able to manipulate specimens straight off the bat in a nice little compact unit, so you can do your imaging then and there. Or some bigger one, that's a robot that actually moves the specimen around for you. The idea was to couple it up to the internet and have somebody else do it from far away. Doesn't really help, there's still somebody who has to put it in. So you're still wasting that time. So it's a cool project. We took some amazing images, but and the last thing that I want to show is about something slightly different, because what we're doing is essentially creating digital data. But we're creating there's limits to what the data that we create, and there's different ways of creating. There's a couple of students here from UCL that looked at improving some of our techniques with multiple light acquisition. And essentially what that means is that they can after the fact, they can start playing around with the light and the shadows in the images, and they can start extracting characters like hair or veins in the leaf, or they can start perfecting some of so stack shot imaging is when you don't have enough depth of field on your camera because you're looking at something that's so magnified. What you can do is you can take multiple shots through the specimen, you can compile those areas of focus in each image, and you can create one big image that has full focus throughout the specimen. Now that requires a lot of time, and you will get artifacts like ghosting or some things that are on top are portrayed as on the bottom. So there are algorithms behind that can help that and perfect that. But usually it requires the data from the multiple light sources and not just a single light source that we tend to use. So with that, that's a bit about the collection, a bit about the digital collections program, a bit about me and the hardware that we use. And with that, I'm going to hand it over to Laurence to talk a bit about all the cool rest stuff.
Thanks, Steen. So my bit is really focusing on the stuff that happens after the image capture and thinking about some of the bottlenecks there. It's not really kind of captured in this, but in all of those labels that Steen was showing you, transcribing them manually takes forever. So I was thinking, okay, how can we do this a bit more quickly? And that's kind of what I'm going to cover. You don't usually think about the museums as having programmers, but we have quite a few developers. We've got a group at the museum. This is just like a very light, trivial thing. We've got a huge PHP project, which is a legacy project, which I'll briefly mention later. But there's quite a few developer teams at the museum. So thinking about Alice, so Steen mentioned this before. What we want to do is get to these images and create a composite image where the pin isn't kind of covering up some of the text, that we can then kind of run it through OCR and kind of process that text. Usually on pinned insects, if we can get to this top label, we can get to most of the key metadata that we're really interested in. But it's been quite a challenging problem. There's a degree of calibration, perspective correction, and then we need to detect the labels, align them and merge them. The detection and alignment has been rather elusive, but we've tried a few different approaches so far. So the first one was using orb to try and find key points between these images and align them. That didn't work so much because we found it very hard to discriminate between the specimen and the labels. The other thing that we tried to do was remove the specimen, but you can see here that the distance of the specimen to the labels is really variable. One of the key issues with natural history collections is their lack of standardisation on the label, on the data that's recorded on the label and the specimens themselves. So that didn't really work either. And then we tried a couple of different RCNN approaches, which kind of worked, but it wasn't really good enough to get the straight edges on the label. When we were thinking about it, theoretically you think of labels as having nice straight edges, but they're made of paper. You've got a bit of paper that's 150 plus years, it will be warped and kind of wobbly. So kind of finding those straight edges is pretty tricky, especially when on this one you've got 1, 2, 3, 4, 5, 6, 7, 8 labels, I think. I think the maximum is 15. So it's kind of working out, okay, which specimens can we actually use on this approach and which ones are just completely not viable. So again, yeah, that didn't really work with the overlapping edges, especially when they're squished tightly together. And then the final one that we tried was combining this with graph cuts, but this was pretty much to the end of our expertise in kind of image processing. And we were having issues with the hue of the background as well on this. So if we were using maybe a different coloured background, it would maybe make it easier. But we're working with quite a big collection of legacy images. So Steen talked a little bit about whole draw imaging. This is a draw of Alfred Russel Wallace's beetles, so a kind of famous collector, some pretty cool evolutionary concepts and thinking about geology as well. And this is a collection of bumblebees, British bumblebees. And this is kind of segueing into another bit of software that we built. You see every one of these bumblebees has got tiny little data matrix barcodes. And we're thinking about these collections of specimens and thinking, what can we do to speed up digitisation? What can we do to speed up metadata capture? So we built a nifty bit of software called Inselect to deal with this. And it's got a couple of algorithms to do edge detection and put cropping boxes around the specimens. It combines automatic barcode reading, but most open source barcode reading libraries are pretty naff and slow. So it works much better when you add in a commercial one. And then each of these images is usually based on a high-res archival TIFF, and you can kind of export low-res versions. And it's got user-creatable metadata files using YAML. So a lot of museums have got different collection management systems, so they can export their own lists and kind of export the metadata with the specimens. So it's used in a whole bunch of things, processing pitfall traps, malaise traps, as well as drawers like this one. And one of our big projects was making an open data portal. So a couple of years ago, the museum decided that it would be open by default, which was a pretty radical change for us. I think a lot of museums are worried about commercial exploitation of their data, thinking about losing revenue sources, so kind of going open by default was pretty radical for us. So all images under a CC BY license and all data CC0. And the portal was how we were serving it. So it's we've got about 4 million specimen records out of the 80 million on there now, and I think about half of those have images with them. And there's also 100 plus data sets. So all of our researchers, there's about 300 scientists at the museum. So if someone's creating data for their research, they can upload it on the portal. And roughly for every single physical visitor we get about 10 virtual visitors. This is a kind of an example of what someone would typically see. It's generally not aimed at a public audience, so it's aimed at more people who want to use the data and just browse the collection, so probably scientific audience. So you've got a selection of metadata, some images, a couple of different views. We've got a couple of sector-specific data standards, and this GBIF is like a big international aggregator, because if you're looking at kind of climate change studies or thinking about Zika, one museum's collection isn't enough. You want to be aggregating millions of those records together for your analyses. So that is the view that we use to kind of send it to an aggregator. It's all open source, it's mostly Python based, and it's based on CCAN, which is a big kind of open data repository. One of the cool things about it is pretty quick at displaying geospatial data. This is a heat map of the Natural History Museum's digitised collections. Some of the cool things that you can see in the oceans are a mixture of historical voyages. So you'll see, I think that's Challenger. You should be able to see Challenger moving around there, which is quite cool. And it's fairly typical of natural history museums. So it's pretty obvious from this that there are huge biases. So usually collectors would collect around settlements or not very far from established settlements or railway lines. So most of these collection points, will, certainly the terrestrial ones, will be not too far from where other people are. They sometimes you go to remote places. And another nice thing about the data portal is that we have version DOIs, so we're one of the first museums to do this. If someone comes along and puts in a query in the portal, when they download that data set, we create a DOI. So if they want to cite the information that resulted from that query, they can do. And it supports RDF, it's built on its own API, and we are trying to do a lot more with linked open data. So you've seen that we've got kind of collectors, so we've got people information, so we're thinking about how can we link up dead and living people. So obviously for living people we're probably moving towards ORCID, but that doesn't sort us out for deceased people, and we've got a lot of them in the collection. This is another kind of a big legacy project. So we host over 1,000 researcher sites at the museum, which are all Drupal based. It's anything to do with biodiversity data, so kind of virtual research and publication platform, because almost all researchers are sitting on unpublished data. And so the idea of Scratchpads was to help them publish without going through the formal kind of academic process, because we're more or less moving away from that model now. But again, it's just another cool thing. You wouldn't think of us as hosting 1,000 sites. That's quite tricky and challenging, and it's a long-running project, and a fair amount of data as well. Half of that data is for a big sound archive project, so recordings of insects and birds and that kind of thing. So we're trying to move towards being a much more data-driven institute, or at least with the digitisation, thinking much more with the data that we're thinking about impact as well. So this is showing records downloaded from the data portal, so you can see a nice steady increase. We've had about 200,000 separate download events in the last 4 years, which I think is pretty reasonable. And you can also see where our referral sources are. So we get quite a lot of people coming in through Twitter. In terms of impact, so most of you kind of from an academic background, so if I'm talking about H-index and that kind of thing, I thought that was probably a safe assumption. So we've been monitoring stuff since 2015, and this is kind of mostly focusing on DOIs, but a lot of our specimens have historically had weird human-written strings that uniquely identify them. And we're trying to move towards having machine-readable barcodes on everything, as well as these old identifiers. But this gives an idea of how many publications are citing our data in the data portal, which is a fraction of what we've got, so it's about 5%. And where the citations are coming from as well, and also with altmetrics to get an idea about, I guess, the public or news outlets are kind of interested in what we're doing. So this is thinking if the collections were a researcher, what would their H-index be? and what are the most popular publications that are citing our specimens, and what proportion of specimens are cited in that paper. And what you see here, because you see these fairly low percentages, these are aggregate data sets from GBIF that I mentioned earlier. So researchers putting together natural history collections to answer much bigger questions, which is also quite interesting to see. Now I'm going to move on to a bit more computer vision and machine learning. So this is so the climate change study that Steen mentioned earlier was all based on kind of British butterflies. And just looking at these, you can see they're kind of similar. They've got a similar kind of layout, the labels are set up on the side. And I was looking at these and I was thinking one day, wouldn't it be really useful if we could group those labels together? Because there's going to be features in those labels that are going to be common when we're looking at data sets of 80,000 or more. And not only that, but many collectors exchange material with other collectors. So if we can start identifying features of labels in our collections, we'll probably be able to identify features in those collections in Paris, Berlin, Stockholm, New York, and start kind of making some models that would be useful for other collections as well. So that was kind of the start of the idea. And this is how it would work through. So I call this concept the specimen data refinery. So at this point we have pretty much no data about the specimen. We might have a taxon name, so which species it is, a unique identifier. This specimen was actually before we had machine-readable identifiers, so it's just literally a string and a location in the collection. So semantically segment the image, so create a mask or find where the specimen is, get the labels out. And in this particular example, I'm just thinking, okay, so if I put out the specimen, what can I do next? A very simple colour analysis, so this is just kind of clustering colour by proportion and thinking, okay, if I'm going to take an average of 10 colours, what do I get? And then thinking, okay, can I do sensible measurements of this specimen? For Lepidoptera, so butterflies and moths, even when they're very, very well pinned, you get wing droop. So it's thinking, does that wing droop mean that if I'm trying to take a measurement on a 2D image, can I correct for that? How good are those measurements going to be? Typically, we'd be interested in this distance here, because wing length acts as a proxy for mass, and mass is a proxy for fitness. So if the caterpillar of a butterfly had a really good food source, then it will be heavier and its wings will be bigger. So you can use that measurement as a kind of fitness proxy. And that was kind of thinking about how I would chain it all together with a set of kind of services to get a kind of enriched specimen data set. And also thinking about the OCR elements as well, because the labels are all unstructured, they're full of abbreviations. You get people names for who collected it, for the taxonomic name, for who determined it. So you've got a whole bunch of people identifiers that you'd like to resolve as well. If you're thinking about paleo specimens, not only are you dealing with locality data of the now, you're also thinking about locality data of the past. So which time epoch was it from? And what did the Earth look like a few million years ago? So you've got a lot of unstructured data and kind of handwritten notes to resolve. So we're looking at a whole bunch of kind of different services so once we've extracted some text from OCR and the labels are doing handwriting recognition, validating that, atomizing that, and giving some kind of certainty value to it as well, which is also a challenge and quite fun. And these are a set of applications that I would hope the data refinery would be able to do without specimens going from easier to harder. So this is a really easy one. This is a microscope slide. The mountain that was used in this slide discolours, it oxidizes over time and goes black, and that makes the slide completely useless. If you needed to go through and remount it, you'd have to take off these tiny glass cover slips and very, very carefully wash the specimen. it is slow and painstaking work. But there are, you can do stuff to prevent that, and if you start seeing partial oxidization, it is easier to intervene and do something before it goes completely dark. And so if we're rapidly imaging the microscope slides, we can very easily just check the hue and see whether there are some dark slides in there. So that's a very simple one. And there are a few other kind of conservation issues that we can see just by colour across different collections. That no one had ever thought about doing that in an automated way before. So we have quite a lot of metadata in our collections, but most of it you saw was in tabular form. And I was thinking, wouldn't it be nice to kind of make some natural language descriptions? So this was the collection I think I was talking to you about. This is from Cooper Hewitt. So they make these nice natural language descriptions with nice links of their collections here. So thinking about how can we enrich our existing data and make it more useful for members of the public, for researchers in collections, because just having tabular data is not really good enough these days. And this is, I guess, the holy grail for us, or at least one of them, is extracting traits. So these are features. So if I can go through and create a set of tools that researchers and curators can go through and train something to be able to take measurements of leaves, or look for phenological data. So is the plant flowering? Is it seeding? Because if you can think, so for orchids, thinking about when they're flowering usually is strongly connected to climatic variables and location. So it would be really, really good data to be able to capture if we could do it from bulk as well. And that, I think, is it. So this is what we're really thinking about at the moment. So how we can do kind of information extraction from images and text at scale. Cleaning up our data. There are issues, so there's not a single ontology for all living things. So if you wanted to get a list of all described insects, there is nowhere in the world that you can go to download that. It simply does not exist. We, as a community, we want to come together to annotate data because, we've got the world specialist on potatoes in the Natural History Museum, but we might not have the world specialist on ferns, but we still have ferns. So how do we start developing tools that allow researchers and curators to kind of work and collaborate together, have multiple versions of the truth, because, some people's hypothesis on what species is might not be accepted by someone else. What kind of automation can we do with extracting information from text, from images, and is it even feasible for us to think about the application of robotics in the collection? Because we need to do things very, very cheaply, but there's so much variety and heterogeneity in the size and shape and storage of the objects that any kind of commercial robot is probably unaffordable at the moment, but we always hope so. Anyway, those are the kind of things that we're really interested in. So if you guys have any thoughts on that, we'd be very, very interested. We've got a few people to acknowledge, so it's a big team at the museum. But thanks for listening. I hope you found that somewhat entertaining and informative.
Questions, sorry?
Your scale of your activity is so huge, doesn't it depress you that you'll never actually get anywhere towards finishing it all?
As entomologists, or starting off as an entomologist, you kind of realise that your work will never be done. So we were focusing on particular taxonomic groups. I was on bugs, you're on moths. And you start off and you think, I will not finish. I will die before the study on this group is done. So thinking about the whole collections is just an extension of that.
I mean, we have a brief an estimate that it's about, I think it's 430 something years.
Yeah, 430 person years.
The problem with that is that our collection is collected over 250. We're still collecting. So by the time we've done for almost 500 years, we don't have twice the amount, but we will have those.
Yeah, so it's dealing with stopping adding to the legacy data issues as well, and kind of training people up. And there's a lot of people that still use spreadsheets very badly for their day-to-day work. And so part of our mission is to get people thinking in a more machine-readable way. So yeah,
you don't run out of challenges.
No.
That's the positive side of it. I will never finish designing contraptions and weird things to solve problems, because there will be enough problems to do that forever. So yes, it's daunting, but then again, it provides me with loads of activities to do.
When you do the imaging, it's basically more 2D image. Have you thought about using stereo imaging to capture 2.5D or viewer-centric 3D type image?
So we have looked at 3D. We have looked at stereotypic imaging. The problem with it is that
I'm going to go back to Alice because I think that's useful as a reference.
Because if you know the camera geometry, you can actually reconstruct the stereo image.
So we have been looking at, one of the problems we have is that the image capture time starts building up, starts becoming, so even the images, so this is just a snapshot from 6 cameras, it's not a problem, but then you have the processing time of that. Even adding the processing time, when you start multiplying that up by 100,000, I'm not saying it's not worth it, and it is something we're looking into.
We had a colleague who did that in Berlin, so they made something that rotated a specimen and took, I think, about it was over 3,000 images of multi.
It can be done, I mean, it's done in industry. So,
yeah.
So we actually capture 3D
But
objects.
with this setup, we have one person, one of our digitisers will process about 1,000 specimens in a day. And this isn't done through any stacking, so it's just one single shot. One of the issues with kind of thinking about partial 3D reconstruction is what is the user going to use it for? So usually, entomologists are interested in genitalia and then a set of diagnostic features, which changes almost by species. And so it's very hard for us to develop a workflow where we know we're going to get the diagnostic character. And in some cases, you can't. They're so
you can
small.
measure your wing angle, so you get, and then you can measure the length exactly.
Well, that would work for some groups, but again, it depends how they're mounted. So you quite often have wings that are bent or crumpled.
I think if it's fine, if we can get a way that's fast enough and usable, yes. If we get more data in the same amount of time or slightly more time, definitely. I mean, there's no reason why not to.
Because you're capturing more images and you're just processing.
But if you look at this one, occlusion's quite an issue, especially with legs and hair. So if you're capturing 2 images, it's still a bit challenging because they're very 3D.
We've had the issue actually with this machine as well, that we're actually generating too much data. Some of our scanners, so the new scanner that we have is creating images that are 200 and something megabytes per image. If we're doing that fast enough, and we're trying to process in real time, because one of the reasons why we try to process in real time, we try to have the person doing the imaging verify the image and the end product, because if they're just blindly doing it and something shifts or something goes wrong, by the end of the day, they've generated 1,000 images where maybe 600 of them are wrong.
We process real-time image on cars as we are moving through the scene, so we can actually do 2.5D real-time. Yeah, but you have FPGA, those things.
Yeah, but it's mostly we're trying to do things very, very cheaply, and we're working. So we're part of a consortium of museums across the world, and there's a lot of small museums that would maybe have a budget that's like £1,000 to create an imaging setup, and so we're trying to create. We try and develop as much open source software as possible. And one of the reasons that Steen likes to prototype in Lego is that it's very easy to create a list of the parts and publish it, and it's usually under £100. So it means that it's open to almost any museum around the world to kind of adopt and use the technology.
Have you considered data corruption and data poisoning? I mean, such a large amount of data, some parts of data that may be corrupted or some malicious people may change the data. How do you detect that, prevent that?
So with malicious data, so our core data is behind all the firewalls and all the security that the museum can provide. So that should be safe. People can corrupt data, and they do it sometimes by mistake. So we have, for example, I think we have, I'm going to have a guess, let's say we have 20 John Smiths in our collection of people that have collected something, but they're not the same John Smith. If somebody goes in and says, these are all John Smith from 1955 to 2010, and changes it, it might change the person who collected tens of thousands of specimens, because it might be a John Smith that lived in the 1800s. When that happens, we actually have a team of data managers whose full-time job is to enhance the data and check the data and fix these kinds of problems. If we're talking about data from the outside, like annotations and things like that, there's a huge problem for us, because if people start doing that, we have to verify the data before we present it.
Well, at the moment, in the community, I think our curators and researchers would want to verify the data, but there's I think a movement where people are thinking about taking a more wiki-based approach. But we need to think very carefully about how we present who is the authority on the data and present certainty data, and even with some of the machine learning approaches when we're thinking about doing classification, thinking about provenance and kind of fair principles and that kind of thing. So we're just starting to get our heads around some of these things and like repeatable workflows. In terms of data loss through corruption, kind of bit loss, for herbarium sheets, we take everything as uncompressed TIFFs, but for the insects, these are typically done as JPEGs. And the reason for that is that it's cheaper for us to redo one of those and kind of do long-term archival storage of the images. We would like to move to complete archival images for everything, but it's just too expensive. Disk storage is still too much for us. And even just like the desktop hardware to kind of. So there's a slide that I thought I might show you, but it's right at the very end, I think. Sorry,
Yeah.
There we go. Oh, sorry. Too much clicking. Hang on. Excuse me a minute.
So the museums are actually just waking up to data preservation at the moment.
Yeah.
That's a big thing now, because we move. I mean, a single image is moved around, I think, 12 or more than 12 times through our system, stored, saved, and replicated, and cleared down and backed up. So when you've done the standard JPEG, when you've done that many times, you start actually seeing the effects of that.
So one of the issues we have with processing TIFFs, so we use some commercial barcode reading software, and one of the things that we did to reduce transcription error was to use barcodes for as many known things as possible and do as much cleanup in the database to create ontologies. So what you've got here is the locality information, its type status. Who in the room is aware of type status? Probably. Okay. So if I were to describe a species, a new species to science, I would designate a type or a series of types. So it's kind of Aristotelian philosophy that this particular specimen represents my concept of my species. And so you have a holotype that represents the whole species. It's got some issues because our concept of what a species is has changed quite a lot since Linnaeus' time. But they're usually the ultimate reference specimen, and you'd usually have a couple. So that's this type field here. A specimen ID, so it's a unique integer, in theory, generated by a collection management system. The physical storage location and an identity. These are essentially primary keys in our database, and this would relate to a species name. And so with some of the software we're using, it's got a limit of reading 5 barcodes and it times out reading TIFFs. And if we're running it on the workstation that the digitisers use, having something that could process TIFFs quickly would be a lot more expensive, so we'd probably have to have decent GPUs in every computer rather than just kind of Dell cheap Dell workstations. So it's those kind of things as we're kind of considering. If we're scaling up to do 80 million, can we afford to have nice GPUs in all of the digitised machines? Those are the kind of constraints we have to work with. It's like having no money and having to do lots of stuff. It's quite fun though, isn't it?
It's challenge. It's about the challenge.
Yes, you have to like working in a problem-rich environment, otherwise you would not be having fun.
So is there going to be a digital version of the Piltdown plan, do you think?
I mean, in theory, there would be at least a. Well, the human remains a tricky one. So generally, we don't make those public. But for certain iconic specimens, I think that there would be public versions of a specimen. That particular one, and I think a lot of the bones and skeletons, for that to be useful for a researcher, you'd want to have CT scans. And CT scans are quite hefty volumetric data. And I don't think anyone in our community has cracked to kind of solve that problem to nicely serve volumetric data in a way that's sustainable and cheap. Yeah. But it would be great to have some of the iconic dinosaurs as well on the data portal. And those 3D models that Steen passed out, it would be awesome to see more of those in classrooms. So if people are teaching anatomy or theory of evolution, to be able to look at different skulls, I think it's a really nice way to interact with the collections. So I think it would be great if we could digitise it. Yeah.
Or to what extent, I mean, you mentioned some of the libraries that are available aren't necessarily very good at the things you want, so presumably you have to code some stuff from the ground up and build it yourselves.
Yes.
To what extent can you reuse existing stuff, and then when you produce your own code and share it on GitHub, do you have a feel for whether other people are reusing the stuff that you've written for other completely different applications?
Yeah, so it's weird stuff. So one of the most used things was actually a Drupal module for displaying tabular data. Was one of the most, I think, one of our most reused things. Some of the modifications we've made to the data portal for displaying geospatial data has been quite widely used. But you kind of don't know. People do stuff that you don't expect with things that you develop. We try and reuse as much as possible because we don't have large dev teams at the moment. We have 4 developers in the informatics team. So 2 of them maintain the data portal, 2 of them look after scratch pads, and then do the innovation work in between those 2 projects. And it's a tiny team. We did have a machine learning specialist, but it's hard for us to retain them on kind of public servant salaries.
You tend to get the students, good students.
Yeah, good students. So we collaborate a lot with universities. So typically with developers, we get early career developers and then late career developers who want to code for fun and don't really care about money anymore.
I think one of the things we have is, when I talk about data sets, machine learning and AI. I mean, we've got more different types of handwriting than most places, but we've got them across thousands of labels. So you've not just got one example of handwriting, you've got multiple examples of the same handwriting from the same person. You've got specimens that, one of our species has 21,000 specimens of that species. So the data, the replication of data is one of the things that we have. And creating data sets for computer vision stuff is one of the things that we can do with what we have.
I briefly mentioned that we've got 80 million. There are about, we think, 2 billion specimens in natural history museums around the world. So, if we make a start with ours, we could make some really useful tools to help the rest of the world. So we're trying to think a bit bigger with the kind of software and data sets that we're making these days.
Your metadata, it looks very graphic. So I mean, I saw Neo4j displayed for one of those things. Do you use a graph database to represent?
So I've been thinking about using it for so long,
Yeah.
but as I showed earlier, I'm not a software guy. So I've built a few smaller database systems.
RDF and things like that are very graph oriented.
Yeah. So I find that I've tried to put our species, so our taxonomy concepts, into a graph database and being able to explore it. But the reality is, unless the user interface is easy enough for everybody to use it and access the data, unless we can get the data into that system, then it will remain something that I do for fun. But I continue to try to find people interested in looking at that challenge and working with it, because I do believe that graph databases have a completely different potential for some of the information.
So we're working on kind of the next iteration of linked open data for the portal. So if we can hook in, so libraries and archives have got really good historical people identifiers. So one of the things that I'd like to do this year is start getting a mixture of people identifiers in on the data on the data portal, and doing a bit more with our geographical locations as well, because then we can do some kind of cross-sector stuff across the wider galleries, libraries, archives, museum sector to bring together data sets. And we're also looking at IIIF as well, so it's used more in the library sector to bring together distributed manuscripts, so illuminated manuscripts, where people want to bring together disparate collections of visual material. So I think there is a lot of potential for kind of graph-like and more kind of IDF stuff with our data, but we're just kind of scratching the surface of that at the moment.
Get Google interested, and they got deep pockets.
Okay, I think we come to the end of this presentation. We didn't have time to discuss while we had some food and wine. And as a sign of appreciation to the speakers, there are sale books.
Oh, thank you.
Which one you selected? I can't remember.
I think that was yours.
Yeah, thank you.
Perfect. Thank you very much.